By the end of this video, we will understand why the integral of the survival function is equal to the mean. Let's get started. You are given the following information about a parallel system with two components. The first component has a lifetime that is uniform on 0, 1. The second component has a lifetime that is exponential with mean of 2. Determine which of the following is an expression for the expected lifetime of the system. For this problem, we need to know a few things. First, we need to know what it means to be a parallel system. So all that means is to say that, let's say you have a parallel system of two components, like we do in this problem. If component A works, the system works. If component B works, the system works. Or if components A and B work, the system works. But if they both fail, the overall system fails. So you need at least one component from a parallel system to work for the overall system to work. And that's what's meant by a parallel system. The next thing you need to understand is how to calculate the mean. So this is, I don't know, I didn't try it this way. I think you could go by with just knowing that the PDF times x integrated is equal to the mean. So that is to say the probability weighted average of x is going to be equal to the mean by definition. You might be able to get by with that information, but it's way simpler to know this property. And I do believe this comes up semi-frequently on the exam, so it's definitely worth knowing. And also, I think it's just elegant. Like, the fact that this is the case blew my mind. I was trying to represent it visually, and I don't know, maybe I'm overreacting, but I think this property is really cool. And that is just the survival function itself, 1 minus the CDF. To integrate that over the domain is equal to the mean. Mind blown. All right, first off, I have the mathy way of doing this. I don't really like this, and it didn't give me a sense of clarity, but I have this included here. So using integration by parts, where you define g and h of x as the following. So 1 minus f of x, which is the survival function, but it's written this way because the derivative of this is going to be the negative PDF. And then h of x is just x itself. When you choose it to be that, it works out to be the integral of the survival function is equal to the integral of x times f of x. But to me, that's not as satisfying as, or in my personal opinion, what I have prepared. So I have a toy example here. So this is a PMF, so there's only 5 distinct values, and there's the probabilities 10% of 1, 20% of 2, 40% of 3, 20% of 4, and 10% of 5. So I just made up these values. And what is the mean? The mean is the probability weighted average. So that is 0.1 times 1, and 0.2 times 2, 0.4 times 3, so on and so forth. A way of representing multiplication visually is with rectangles. So instead of just doing that with, the math calculation, we could also represent it visually as the area of a rectangle, side lengths 1, and then 0.1 for this first bar, and then a width of 2 and height of 0.2 for the second, and so on and so forth. So scrolling down, I have that here, and I actually chose to start with the furthest to the right point. So what's the largest value? 5, so it's going to be width 5, and height corresponding to its probability. And then I just stacked all of these bars on top of one another. So we know that the mean is just the sum of the area of all of these rectangles. And for this y-axis, I have question marks because at this point we're just visualizing x times f of x. This isn't, we're stacking things arbitrarily. Doesn't really, we don't know what this means yet. But this is actually just the survival function. So just getting rid of the colors, I just changed the y-axis to be s of t. So going back to these visuals, and let me zoom out so we can see both of them at the same time. Somewhat. So the reason that this is the case is, let's take the example of 1. So up until time 1, everyone's alive, and then at time 1, 10% of people die. And that's represented by the death rate at that value of 10%. So the height of the bar corresponds to the death rate at the given x. And then the reason why it's the survival function is the height corresponds to the number of the sum of the height of everything below it that extends out further. So that would include the height that corresponds to 2, because 2 lives past 1, and 3 lives past 1, and so on and so forth. And so the height of all these other bars is 0.9, and that just corresponds to the survival rate of 0.9. So I feel like my talking is probably more rambling than usefulness, but I feel like this visual does a good job of representing why the integral of x times f of x is equivalent to just the integral of the survival function, because when you stack the bars as such, you just get out the survival function curve, and then obviously the area is just the sum of all these areas. And then also, this is obviously it's an informal proof. You could take the limit as your approximation of rectangles gets to width 0 for a continuous function, right? Because you could approximate it in the same way that integrals are derived with limits to get at something similar. But hope you find this as interesting as I do. I think this property is really cool. It's just elegant. The integral of the survival function is the mean. I think that's pretty neat. But enough of that. I'll jump into the problem at hand. And actually for this problem, the first thing I want to say is kind of the way that I strategize for these problems. At least if I'm being, good, sometimes I'll jump right into it against my better judgment. But what I like to do for these problems is actually try to solve it without looking at the options. So for these kind of more conceptual problems, but where there is a way to just calculate what they're asking for, I try to calculate it, and then once I have something, I then compare that to my options A through E. So with that in mind, we'll jump into it. So first off, I just copied and pasted part of the problem. So these are the two components that are in parallel, uniform and then exponential. And then I'm defining the survival function for the overall system. So the overall system survives so long as one of them survives. And we don't like that. There are 3 different ways that the system can work, and that's too complicated. So we're going to do 1 minus the only one way that the system can fail. So the system can fail if both components fail. So we're going to do 1 minus both of them failing. And failure rate is 1 minus the success rate, so that's why there's a bunch of 1 minuses here. But this just works out to be 1 minus each of them failing. And the failure, the probability of failure is just the CDF. So F works both ways as the CDF as well as the failure. So first off, we have our uniform distribution. So the CDF for uniform 0 to 1 is just going to be x, right? The CDF at 0 is going to be 0. The CDF at 1 is going to be 1. And we know it's a continuous, it's just constant linear for the CDF because it's uniform. So we just know this is x. If it was something more complicated than bounded 0, 1, I think you could still apply that logic, but if you don't want to, uniform is just a beta distribution with parameters 1 and 1 for alpha and beta. The second thing to note is we're going to be multiplying the CDFs of A and B. So we actually also need to define our CDF for uniform beyond values of 1. So when x is greater than 1, it just is 1, because it's always going to fail by time 1. And then second, we have our exponential. So the CDF of an exponential with mean 2 is just going to be equal to 1 minus e to the negative x over 2. So now with that, we can jump into the actual integration and using that survival function property. So we know that our survival function is 1 minus x times 1 minus e to the negative x over 2. And so we just have that written out here. But we broke it up into 2 components. So I apologize, this 0 right here in this integral should be a 1, not a 0. So from 0 to infinity, we can break it into the 2 components, 0 to 1 and 1 to infinity. And for that 0 to 1, it is just as I said, it's going to be x for the uniform because it still has a possibility of being successful or failing, so it corresponds to x as we solved up here. And then on the right, it's just always going to be 1 for the uniform. It always fails by that time, but we still need to check that exponential distribution. Then scrolling down, I think I just accidentally copied and pasted this without deleting the first one with the incorrect 0, so I apologize for that. So we'll go to the third line here. So at this point, what do we got going? So this is pretty much what I solved for. I got to this point, and then I started looking at the answers. And the answers had 3 integrals instead of 2, for the most part, I believe, if we scroll back up. And so, yeah, I know that this isn't right. And so I can see based off of the other options that they break it up into further integrals. So then going back down, I say, well, how can I break this up? This 1 to infinity integral is pretty much locked. There's no way I can break this up. But there is a plus sign here, so I can probably break this up into its 2 components. And when I do that, I also have x's instead of t's here, but it's the same thing. This final answer that I have here, after I split this integral into its 2 components, just is one of the options. So we see that as option A. I really don't like these problems because there's just so much to look at. It's hard to digest. And even having that written down below, the amount of time I'm going to spend on the exam making sure it exactly matches this, and there isn't a slight difference in, you know, the limits of the integral or something like that. Definitely a nuisance, but hopefully that helps. I like to approach these problems by trying to solve it and then comparing whatever you come up with their options, and sometimes that'll also help you catch a mistake you might have made. But yeah, so solution is A. That concludes today's video. If you find this helpful, please consider subscribing, liking, or commenting below. Thanks for watching.